Okay, we're going to start today talking about rolling motion. And rolling motion occurs in two ways. And it's really going to develop kind of three scenarios for us. We'll be looking at all three of them. We'll look at the first scenario tomorrow, and we'll look at the other two scenarios. We'll look at the first scenario tonight and the other two scenarios tomorrow. First, if you've got a rotating object and we treat it like this one's going to be a disk, so it'll just be rolling along a surface. It's got a radius, the edge of it is moving at some velocity. And remember, we usually describe the rolling velocity, or the velocity with which something's turning, not with v, the velocity of the edge, but rather omega, the angular velocity. And remember that omega r is equal to v, the velocity of the edge. So omega, whenever we want to describe how fast it's turning, that will be the velocity of the edge divided by the radius. But that's not the only kind of motion this guy's undergoing. It's also translating, so it has a second velocity. From the center of mass outward, there's a second velocity. That's sort of its translational velocity. So let's write it as a vt. Vt would be the regular kinematic velocity that this would have, same as a block sliding on a frictionless surface. That would be basically how we would judge its motion. Its rotational velocity doesn't tell us a lot about how fast it's moving, because these velocities may in fact not be interlinked. Rolling motion is always about what's happening between the surfaces. If the surfaces are frictionless, then whatever it starts rolling as, whatever its rotating motion is and translating motion, it's going to maintain those values on a frictionless surface. If I push on the center of mass, Vt will go up, but the rotational velocity won't change. And if I give it a torque, that torque will cause it to rotate faster, but depending on the angle I come in with, it might not cause it to translate any faster. So we would treat both of those as separate dynamic problems and kinematic problems. But if this surface has friction on it, that means these guys are going to interact with each other. And they're going to interact in the following ways, and this is what separates these scenarios out. First, these could be in lockstep. That is, this point of contact with the ground could always be stationary. And the only way it can be stationary is if while the disk is turning, every time it sort of plants its foot on the ground, there's no relative motion between those surfaces. So it's rolling just fast enough to maintain its linear velocity. It's not either overspinning, nor is it underspinning. And those will be the scenarios we look at tomorrow. For today, though, we will assume that all rolling motion is rolling without slipping. And that's what they refer to it as, is rolling without slipping. And when that's the case, there is a relationship between these two variables. Notice as the center of mass moves at Vt, the bottom, this point of contact with the ground, doesn't move at all because Vt is given in relationship to the ground. That's its frame of reference. So the bottom of the wheel doesn't move at all. The center of the wheel moves at Vt, and actually the top of the wheel moves at 2 Vt. It has to move twice as fast because it's going to catch up with the front edge, become the front edge, and then become the new point of contact with the ground. And the only way it can do that, the only way this can basically beat the center to this point over here is if it's moving faster along the top. And it will. It'll move faster, it'll end up on the front, but then from that point onward it will slow down to 0, which is why it will end up stationary when it hits the ground. Okay? Because of that, that means the rotational velocity, which never ceases, this v, this rotational velocity, it's constant, which means the point in contact with the ground is still moving with an angular velocity of v in this direction. So that's where we get our relationship. If the angular velocity at that point, tangential on the edge, is backwards at v, but the translational velocity of the entire object is forward with vt, the only way the speed of the point on the ground can be 0 is if these two quantities are equal. So when an object rolls without slipping, that means the magnitude of its translational velocity equals the magnitude of its rotational velocity. And that's the condition for rolling without slipping. We're going to look at one or two examples of this, and that's basically when an object rolls down an inclined plane, and we want to see what speed it gets to at the bottom. Okay? So let's start with that same disk, and we're going to roll it down an incline This incline will be at an angle theta with a length of the incline of d. So we're going to start at the top with a disk, and this disk is going to roll down without slipping. That means the point of contact with the ramp will always be at 0 velocity. And what that means is the radius of this guy is going to control how fast it rolls down. Because it's a disk, that's going to help control it as well. And we're going to basically solve this guy as a conservation of energy problem. My goal is to figure out how fast is the translational velocity at the bottom. So how fast is the disk moving when it reaches this point right here as a result of rolling down this incline? Well, first we got to do a little trig, the height we're going to need for kinetic energy or for potential energy. So this is going to be a sine ratio. Opposite over hypotenuse is h over d equals sine theta. So that means h equals d sine theta. I know that at the beginning, when it's stationary at the top of the ramp, the entire energy, delta E, is going to be 0, but the total energy at the top, E initial, is going to be equal to UG, or mgh. Now at the bottom of the ramp, we're going to have all E final energy, and that's going to be two kinds of kinetic. It's going to be the kinetic energy of translation plus the kinetic energy of rotation. We already looked at both these formulas, so I'm just going to fill them in right now. That's going to be 1/2 mv squared, and this will be this translational velocity, plus 1/2 I omega squared. And this will, of course, be a function of the rotational velocity, but as we saw in the last video, when this guy's in lockstep and it's not slipping, the translational and rotational velocity will be in lockstep too. I'm going to do some doctoring of this formula before I set up the entire relationship, and that is 1/2 mvt squared is also going to be expressed in this guy. So I'm going to fill in the moment of inertia. It's going to be 1/2. The moment of inertia for a disk is 1/2 mr squared. And then finally omega, because the translational velocity is equal to the rotational velocity under the condition of rolling without slipping, and the rotational velocity is equal to omega r. That means omega squared is equal to vt squared over r squared. So take a look at that for a second, just to make sure you get why we've got the 1/2 mr squared is I, and the vt squared over r squared is just what omega is under the condition of rolling without slipping. So now we can do some simplifying here. That's 1/2 mvt squared plus, this will be 1/4. We've got m, the r squareds cancel, so that's mvt squared. So that's going to be 3/4 mvt squared, and that's what mgh will be equal to. So if we write out our whole statement of conservation of energy, it's mgh or mgd sine theta is equal to 3/4 of mvt squared. The masses cancel because the speed this reaches at the bottom should be a function of its shape. It should be a function of the height that rolled from. It should be a function of its moment of inertia, which is expressed inside this 3/4. But it shouldn't really be a function of its mass, because gravity acts on mass with a force proportional to the size. And of course, kinetic energy also contains mass. So they should and do cancel. So I'll put the 4/3 on the other side. So vt squared equals 4/3 gd sine theta. And the final velocity at the bottom of the ramp is going to be the square root of 4/3 gd sine theta. Now, if we in fact change the shape, suppose this was a marble instead. Well, a marble is going to be a sphere, and a sphere has a moment of inertia of 2/5 mr squared. Or it could be a hoop with an empty center, in which case its I would be mr squared. So you can see that depending upon whether it's a solid disc like this one, or an open hoop, or a marble, that'll certainly change the coefficient here, but everything else will remain the same. It's always going to be some function of GD sine theta for the velocity that a rolling object has after coming to the bottom of a hill based on rolling without slipping. And again, that is featured right here. Without that idea of rolling without slipping, this condition wouldn't hold, because the translational velocity and rotational velocity do not have to be in lockstep. They're only in lockstep when the point of contact with the ground has no relative motion.